I've started the camera. You need to be quiet because otherwise the camera will pick up all your conversation instead of picking up what I have to say. And what I have to say is, I don't know if I label it that strongly, but I want it to be filmed for posterity. All right. Okay, come on. Why aren't you working?
Oh, it has trends.
All right. So, we are going to cover two topics today. Both are pretty small topics. Well, you got the star mix over there? That's good. I like the star mix. All right. So, we're going to be covering two topics today. The first one is uniform circular motion. Really simple, straightforward, not that big of a deal. It's one of those things that I actually would have covered this in one day anyways, because it's a really simple thing. There's basically like an equation you need to know, and that's it. Once I cover this, we'll cover simple harmonic motion, which I didn't even cover at all last year, because it's only like 6% of the test. So we'll sprint through that, and then we'll move on. Cool? Okay. All right. So, you don't need any of these things. You don't need that. All right. Okay. So, covering the basics of uniform circular motion. Let's start by kind of defining what uniform circular motion is. Hello. Did you check in on your way in? So, uniform circular motion, if you can't tell from like the definition, like just the phrase, what it means is it's motion around a circular path at constant speed, which means there are really like two important ideas to this definition. The first one is that there is a circular path. That's probably the obvious part. The part that people don't always pick up on is the constant speed part. Over the next few days, and actually I might not be here tomorrow. My baby is sick and we're trying to decide if I should stay home or if I should stay home. So what we'll cover, if not tomorrow, like in a day or two next week, is we'll talk about like all the other circular motion. So like uniform circular motion is this kind of like special case that this is how it works. And it's the simple case. When we do all the other circular motion stuff, that's where it actually gets more complicated. So you'll see us take a slightly different approach to that. So just hang in there for that discussion. So question, can an object traveling a circular path have a constant velocity? No, it cannot. It can't have a constant velocity because the direction would be changing, right? So we have this important idea that we talked about before, that when we look at velocity, it's a vector. It has a magnitude and a direction. So if the velocity is changing, what does that tell me?
It's going to accelerate.
Yes. What?
It's accelerating.
It's accelerating. And if it's accelerating, what does that tell me?
It's speeding up.
Velocity.
Yes.
There's not a constant answer.
We already knew that. If I have an acceleration, according to Newton's laws, that means there's also a...
Velocity. Gravity?
No.
Opposing. Change in direction.
This is why I'm quitting. This is why.
Okay, you know what? We didn't want to be together.
You know what? I'm quitting too.
Yeah.
Yeah.
I just
Do it.
quit last week.
Just drop out. Education's overrated.
I considered it. Mom said no.
No, you really shouldn't. Guys, that means there's an unbalanced force, right? There's a net force on the object. Okay? Remember all like Newton's second law, the net force is equal to mass times acceleration. So what I would know is that the velocity is changing because the direction is changing. And if the velocity is changing, that means I have an acceleration. And if there's an acceleration, that means that there is a net force on this object. So every time we look at something moving in a circular path, there's an unbalanced force that's happening there. All right. Okay, so let's get into some of the terminology here. We'll come back to that unbalanced force bit in a moment. When we start talking about the terminology, we've got two bits here. The first one is that because the direction of our velocity is always changing, I need a new kind of term to talk about that velocity. And so we make it this new term of a tangential velocity. You should be familiar with the idea of a tangent line, meaning that it's touching the circle at exactly one point. That's what's going on with an object that is moving in a circle. If you cut the string at any given moment, it would continue in a straight line tangent to the circular path wherever it was. Okay? So, if you, I think I already said most of these things. If you imagine that point right there, then the velocity is there, right? It's tangent to the circle from that point. If you imagine 3 other points where that might be happening, you can imagine the velocity is in all those places. So that velocity is constantly changing. Glad you did that super smoothly. All right, so important to understand the magnitude of that velocity stays constant the whole time. The direction is what's changing as it goes around the circle. Now, because this is happening, there must be some sort of acceleration, right? The acceleration, to keep it in a circular path and only change the direction, must be perpendicular to the circle at any given point. If it was this way, then it would be changing the direction, but also adding a little bit of speed. If it was this way, then it'd be changing the direction, but also slowing it down a little bit, right? Because I would have some sort of component that's pulling it, and some sort of component that's making it speed up or slow down. Does that make any sense? So that means that at any given point, the acceleration must be perpendicular to the tangent line. And if it's perpendicular to the tangent line, then that means it's always pointing towards the center, which is why we call this a centripetal. Centripetal literally means center pointing acceleration. Yeah?
Is that the same thing as when you're on a merry-go-round and you can't jump in the middle?
Okay, so I'm glad you asked that, because this is something I hadn't even thought about but is worth addressing. So there are 2 terms used in physics that are somewhat related but not the same. Those terms are centripetal, which is this, and centrifugal, or sometimes what it should be pronounced really is probably centrifugal, because that is what makes more sense. But people just say centrifugal. Those words sound the same, and for good reason. So let me briefly address the other word. So centripetal means it's pointing towards the center. So in any context, if I say something is centripetal, that's what I mean. In this case, I'm talking about that particular acceleration. It is a useful concept, because here's the deal. When you're in the merry-go-round and you try to jump towards the center and you get pulled back out to the outside, what's actually happening is that you are moving inertially tangent to the circle. And so when you jump this way, you're actually still moving that way. But from your perspective, it feels like you're getting sucked back to the wall, when in reality, you're just moving, you're moving this way, but there's a wall there again. Does that make any sense? I mean, maybe if I drew a picture, this would make more sense. So here's the merry-go-round. Here's you, right? Your velocity is here. Does that make sense? If you jump this way, then let's just say you added velocity that way. Cool? Which means you're going to have a velocity that's actually these 2 added together, so somewhere this direction. So what happens is you jump towards the center, but you end up colliding with the wall again over here. And you basically end up taking this arced path as you do that because of those things. And so your perception is that you got pulled back out to the outside. But the reality is you added a velocity perpendicular, but you were already moving tangent, and so you just moved exactly where you should have moved. Does that make any sense at all? Now here's the deal. That kind of brain teaser way of thinking this through is confusing and frustrating, and so engineers actually have a term where they make up a fictitious force that would cause you to be pulled to the outside. That fictitious force is the centrifugal force. It's not a real thing, but let's be clear, it's not a real thing, and it's not useful for classical mechanics, which is what we're learning here. But if you're designing a clothes washer or a merry-go-round or whatever, it's actually more convenient to imagine that there's a force that has the same properties that I just discussed here. Does that make any sense? So all that to say, in AP Physics 1, we never used centrifugal force. You may see it other places. Some physics teachers go so far as to say that it's like dumb and should never be used, and I think that's missing the point of like why that term exists. So I try to tell you, like, if you're an engineer, there's some places you might use that term, but in this class we don't ever use it. Does that make any sense? But that centrifugal effect is actually why, like, one of the techniques that we've at least imagined in science fiction, to my knowledge, it hasn't been used. But it's totally, in theory, a thing that you could do, is if you take like a space station and you spin it, then it can create an artificial gravity because this centrifugal effect would work, right? Like if something, like if you're standing here and to you up is into the middle of the circle, well then when you jump upwards, this effect happens where you jump upwards, but you already were moving that way, and so you end up landing back where you were because you're spinning at the same rate as the circle is. Does that make sense? So you end up landing back where you were. So from your perspective, there appears to be gravity that doesn't actually exist. There's weird stuff that happens with that too, though, because there's this thing called the Coriolis effect, where like that effect isn't as strong towards the center, and like weird stuff happens. One of my favorite science fiction books that your dad also reads, so you know, shout out, understands this all really, really beautifully. And one of the things that you would notice is like if you're pouring a drink, it would be much harder to pour that drink correctly, and you would notice the stream not falling, but actually bending because of air resistance. So it's a fun thing, right? There's all sorts of cool stuff that comes up with it. That was a long tangent to answer your question. I'm not even sure I answered your question, but hopefully we had a nice conversation about merry-go-rounds and space stations. Did I answer your question at all, or did I just say a lot of confusing things?
No, you got it.
Okay, cool. All right. Anyways, so back to this class, right? So in this class, important point, we don't use the centrifugal force because it's basically a made-up thing that has an application somewhere else, right? For this class, we talk about centripetal acceleration. And again, the idea is as this direction is changing, I need just enough acceleration to change the direction, but not so much that I change the velocity of the object. And so what that means is that I need that acceleration to point exactly perpendicular to a tangent line, and perpendicular to any tangent line on a circle is towards the center. And so that's where we get this idea of a center pointing force. So if you imagine like this guy on the, like at the 3 o'clock, pointing towards the center would be to the left, right? But then there's 3 other places you could think of where pointing towards the center is a different direction. Bless you. And so we see the same thing as before, where that center pointing acceleration is just changing directions the whole time. Does that make any sense? Okay. All right. So, and again, the magnitude's going to stay the same. It's a constant magnitude. It's just the direction that's changing. So that brings us to the math, and really there's just one equation you need to have here. So what this equation is doing is it's comparing the centripetal acceleration with how fast you're moving and how big the circle is. So Vt is the tangential velocity, and r is the radius of the circle. Okay? Now, that gives me a convenient way to find what that centripetal acceleration could be, right? It also gives me a convenient way to find what the centripetal force would be, because we know there must be some force that's causing that acceleration, right? You cool with that idea? And so then I could use this to find what that centripetal force must be. But I want to take you back to that original conversation, right? If I'm in a circular path, then the centripetal force is not a singular force, it's the net force. It's the overall effect. So it could be because of one thing, it could be because of several things. Does that make any sense? So we're not introducing a new force type, we're more introducing like a job that a force or forces could be doing. Does that make any sense? Like, let me give you an example. Let me give you 2 examples actually. One example would be, have you guys ever seen those machines, like the fair rides that like they spin around, and they spin so fast that you stick to the wall, so they can like pull the floor out from under you, and now you're just stuck to the wall. You guys seen this? Okay, so, no? You ever seen this thing? Well, that's what happens. So, when you look at that kind of device, right, the force that's providing the centripetal force there is the normal force that the wall is exerting on you. And the reason you don't slide is if I spin you fast enough, I can make that normal force large enough so that the frictional force is large enough that you don't slide down the wall. Does that make any sense? Because remember, friction is equal to mu times the normal force. So if I can bump that normal force up really high, then I can make the friction really strong, and then you don't slide down the wall. Does that make sense? But what's important there is that the normal force is what's providing that I almost said the wrong thing. The centripetal force that's keeping you from sliding out. Does that make sense? Okay. Let me give you another example. You're on a roller coaster, right? When you're on a roller coaster, it goes up and it goes around a perfectly circular loop, which, by the way, they don't do because it hurts people. And you'll see why as we talk about it. When you go through that perfect loop, right? Well, what's happening is at the bottom of the roller coaster, your free body diagram. I'm not going to erase this Christmas tree. I'm sorry. It's too beautiful. It's got to stay. What's happening as you go around the loop, so here's a loop, is that at the bottom, your free body diagram looks like this. You've got a normal force and gravity. So in this case, the centripetal force is the sum of these two, where they disagree in direction. Does that make any sense? Okay. If you look at a point like this, then your free body diagram is that you have gravity down, and you have a normal force, which is towards the center, because that's where the seat of the chair is, right? So in this case, the centripetal force is only because of the normal force. And then at the very top, your free body diagram would look like this, where now gravity is still pulling down, but the normal force is also pushing you down. And so now the centripetal force is the sum of those two where they agree in direction. I like this example because the point is that this center pointing force is made up of different combinations of forces for the whole loop. It's not like one thing that's keeping you in a circular path. It's like things are changing jobs. Yeah?
So, you know the ride at the fair where it's like the fireball and like it just goes in a circle the entire time? Like you just...
I don't go to the fair because it's gross.
Well, it like, it's straight up just a circle and you go in a circle the entire time. Like, is it the same thing?
I would assume so,
Okay.
if I'm understanding you correctly.
Yeah.
The point I'm trying to get at with this is when you're looking at doing a force analysis on something that's traveling in a circle, you should not just jump in to say like, all right, what's the centripetal force, as if it's like one thing, right? Like we see in this case, there are different forces that combine to do that thing. You follow? Okay. Now that's really it. That's all you need to know about uniform circular motion. Okay, so uniform circular motion, you have a thing moving in a circle at uniform speed. That means it's got a velocity that's tangent to the circle. There's an acceleration that's pointing towards the center. If I look at that acceleration, I can use this equation to find it. And if I want to know what the centripetal force is, then I just multiply that centripetal acceleration by the mass of the object. Because that's just Newton's second law, right? The centripetal acceleration would be due to the net force, always. Does that make sense? Mm-hmm. Questions, comments, concerns? All right, that's it. Okay, let's do this one.
Do you need to make another video?
I do, thank you. Was that what you were going to say? Just something else. Thank you guys for your reminders.
No, it's so good.
Why do you have your